So we're very happy to have Donald Lyndon Bell visiting us again. He visits us every several years. I'll keep that up for a while here. I just was looking on my phone to see his CV, and I learned something of interest to me at least. His advisor was Leon Mestel.
Who's still alive and is still in Cambridge.
I knew his son, Ben, actually pretty well.
Uh-huh.
I used to live in London, yeah, so that was a lot of fun. So now I understand a bit better why you're obsessed with magnetic fields. Yeah, I used to work on that sort of thing quite a bit. Anyway, as you know, that he's in town partly for the showing of the film Starman, which is going on through the beginning of March. So if you didn't see it in the opening, Thursday night, Friday night. Mm-hmm. You can go see it still. He's going to tell us today about thought experiments on relativistic gravity.
Thank you, Norm. It's a pleasure to be here again, and I'm not going to set you the same problem as I set you the last time I was here, which is a problem that relativists get wrong, so you're all right. You're not going to be examined today. The universe is accelerating, and we believe that this is due to the stress parts of gravity. And I found I didn't really know how stress gravitated. So this is partly to get you familiar with the other parts of Einstein's equations, not the mass part, but the stress part. And if any of you feel very stressed out already, that's your business. But it's the stress part that's due to the fact that this thing has to support my weight at some stage or another. Well, all parts of the matter tensor gravitate. So by Newton's law of action and reaction, all parts of the matter tensor must respond. It's not just a mass responding, but it's also the other parts of the matter tensor that respond. And the other thing that you'll find constantly in life, people telling you that they're going to revise or change Einstein's law of gravitation. There are two ways of doing that. There's the way that says, I'm just going to take a different law, but nearly always, not quite always, but nearly always, you will find that if you change T mu nu and leave Einstein's equations exactly as it was, and as you don't necessarily know all the contributions to T mu nu, you can say, well, Einstein was right, but it's just a new contribution to T mu nu that you're talking about. So I'm rather of that school, that I really believe that nearly all the time when people talk about a new theory of gravitation, they mean a new extra element to the T mu nu. That's just as a... Now, these are the things that I hope to talk about. Gravity pulls on energy, not just on mass. Pressure increases gravity, but actually flattens space. Tension does the opposite. It repels gravitationally, but curves space. And I want to illustrate these things by different solutions of Einstein's equations. Energy currents give gravomagnetic fields which act on moving matter just like magnetic fields act on electric currents. Relativists have a very bad way of talking about this. They talk about the dragging of inertial frames. It is much better to think about gravomagnetic fields. So think, whenever they say that magnetic fields are dragged, don't translate it into the gravomagnetic fields that are about. And while parallel electric currents attract electrically, well, like charges repel, like masses attract. So it's hardly surprisingly that parallel energy currents repel instead of attracting. And the gravity and gravomagnetism of light, I will talk about a beautiful paper of Bonner's, which I think you ought to look up, because it really is a lovely paper. It's the gravity of light beams. You know, most of you think about the bending of light, and you think about a heavy mass and a light beam going past it. You can perfectly well think about it the other way. You think of a light beam and a mass which is attracted by the light beam. we'll get to that. Anyway, space is twisted, and this was something that I think was not really known before, but is interesting. And I may then tell you at the end why everything I say is subject to a bit of problem. But we'll see whether we get time enough to do that. These are the people. This is Benjamin Franklin, Joseph Priestley, Ampere, and Faraday. But those are the people who did experiments which led to Maxwell's equations. Now, as we'll see, as you know, there were people who did things in gravity. Newton. The Reverend John Mitchell, you'll find his name spelt many different ways. He probably spelt it many different ways. But I happen to go to where his signature actually was in the Royal Society book in which he signed his name. And that is the way he signed his name in the Royal Society book. So I think that is the way you ought to spell it. But if you look up Whittaker's History of the Theories of the Ether and Electricity, he doesn't spell it that way. His name is rightly underneath his friend, who was 10 years younger, Henry Cavendish, and they were very close friends. And Henry Cavendish, of course, was a member of a very aristocratic family, and he didn't like being distracted from his work by sex. And so he didn't want to see a woman. And so one of the conditions of maids in his establishment was if they were ever seen by him, they would be dismissed. Pretty radical. Anyway, that was the way. And he, of course, most people don't realize that Mitchell invented the apparatus to measure capital G. He was a bit doddery by the time he got it all assembled. He didn't manage to make it work, and eventually Cavendish begged it off the person to whom it was given, and Cavendish then made it work and measured capital G for the first time. But it's actually Mitchell's apparatus and Mitchell's torsion balance that was doing that. Anyway, it got on to Einstein, as you all know, and that we ought to get on. Now, there's a few preliminaries about what we call force. In Newtonian mechanics, it's just the rate of change of momentum with respect to the time, and that's the value you get, of course. In special relativity, you write a four momentum, which contains the energy as its fourth part, and you find that you've got an extra factor in what you call the force. So the relationship between the three components of the force, which is when it's mu, when it's Greek, it'll be a 4-vector, and when it's in what do you call it? Non-Greek, anyway. It's a 3-vector, and this thing's the 3 force, and this is the 3 part of the 4 force, and they're related. And I will be talking about these forces, which are the ones you really feel. And in general relativity, well, if you're talking about something like Schwarzschild's metric, I will write it with this coefficient called xi squared there, and I'll write something like that for in Schwarzschild's case, this would be the same. This coefficient would be xi to the -2, but in general, for a spherically symmetric distribution, that would be different. What you call the radial component of velocity, or the radial velocity, is just the local increase in distance, which is given here, divided by the local increase in the local time, which is given by both those. So that's what you do, and I'll sometimes write psi is e to the minus psi. This psi is like gm over r. It's the thing that's very similar to a Newtonian potential. And of course, xi squared is this thing. Right, well, let's get on. This is a very important statement. A lot of relativists tell you there's no such thing as gravitational force. And the easy way of proving them wrong is to say, look, here I have a book, and I have a force that pushes upwards. And if I remove the force pushing upwards, it drops. So in any stationary case, I can measure the gravity field on that book by measuring how much force I have to push up with. That's not true in general, and that's why relativists don't like it, because in a general non-stationary case, it's not clear what stationary, what static means. And but I will be talking about that. And Landau and Lifshitz develop a whole lot with respect to this, and this I consider is the best book, The Classical Theory of Fields. I consider to be the best book on general relativity. And when Chandrasekhar wrote a review of that great fat tome that you all know about, he basically said this book manages to do in 850 or something pages what Landau and Lifshitz managed to do in 150. And that is sort of true, but I think actually Landau and Lifshitz have rather more in it, but that's another matter. So I'm a Landau and Lifshitz man, you can see from that. One of the things that Landau and Lifshitz do is for all stationary spaces, they decide that it's a good idea. Is there a pointer or is there not?
There is.
Oh, that's excellent. That's just what I like. Landau and Lifshitz, you see, you can always take the mixed terms between dt and dx and make them into a perfect square like that, and then put the rest into something else. And this is, you can do in all stationary cases, and Landau and Lifshitz do this, and then look at one of the interesting things is in any stationary space, you can change what you think of as the 0 point of time in a position-dependent manner, and then compensate by changing A. And then everything else is the same. And if you do that transformation, psi is independent of that transformation, gamma is independent of that transformation. The thing that changes are the A and what you're calling T. Now that has a close analogy with gauge transformation in electrodynamics. And why I call this thing A is it's like the 3-vector potential. And Landau and Lifshitz point out that the most important things, the most physically important things, are sort of independent of this transformation. And so they put store on gauge invariance, which means that you can, as it were, change the cuts through space-time that you're making in a position-dependent manner. And that is an interesting way of doing things. Well, at rest, for velocity u has this form, if you're just looking at something, and a 4 acceleration is like this, and that comes out to be just this thing. This is for a static metric, actually, with A. Well, actually, well, if we're at rest, it doesn't matter. So it's just this thing that gives you the 4 acceleration, and from that you can get the 4 force, and therefore the 3 force, and necessarily to hold it there. And if you do this for Schwarzschild's metric, well, I've done it for Schwarzschild's metric with a lambda term in there, because lambda terms are now the rage. And so if you do it for that, then psi squared is this thing, and E is just E. Some people would like that called little g. I've called it E because it's analogous to the electric field, but it is a gravitational field. I'm just making an analogy between electricity and gravity, and between magnetism and gravomagnetism. So whenever I write E and B and things like that, it's all gravitational. It's nothing to do with electricity. But I want you to see the analogies, and therefore now, if you look at this gravitational field worked out from this way, you find that this is it. And, you know, this bottom is nearly 1 if you're in, if it's not very relativistic. And so you get Newton's law minus m over r squared times the unit vector. So this is the basic attraction, but it gets this bit that is proportional to distance if you have a lambda term there. But one of the things that you ought to realize, and is very important, is that that this term is not really, in a sense, caused by the mass that you put there. Because if you put the mass equal to 0, the lambda term would still be there. So it's not as though the gravity is modified by this, the gravity of an object is being modified by this lambda term. It's the lambda term is actually just like, I think that's probably on the next slide, let's see. Yes. For m equals 0, there remains a repulsion, and that's a repulsion like a uniform sphere of this density. So if lambda equals 0, the tension at infinity in a string is, oh, that's irrelevant. But if a test body is forced to move radially now, we can actually look at what's happening to this force. And the interesting thing now, we're forcing a body to move radially at constant velocity. And so we find that the 3 force is still there, and but it is actually larger by this factor. If we make it move radially at constant velocity, we actually get this enhancement, which is telling you that it's, as it were, the energy that is being pulled rather than the mass. If we move it tangentially, we then get an expression for centrifugal force. And here we are. You get this thing times v phi squared upon r for measure around the killing vector of you get an expression for this centrifugal force. And you'll see here that because your h here, your angular momentum, has some of these 1 minus v squared over c squared terms in it, that actually here is, as it were, this energy. If you write it in terms of h, it has this extra factor, 1 minus v squared. And this is actually rather important, because it's telling you when v approaches 1, that the force is, I mean, you know, even if you take that into account, the force is going down. As it were, the centrifugal force is going down. And therefore, that allows a gravitating mass, despite the angular momentum, to pull it right into the origin, which it wouldn't do Newtonianly at all. So it's really that this extra factor, 1 minus v squared, because the h is constant, and that is in there, that is allowing the central, is allowing a black hole to swallow something with angular momentum, let's put it that way. Now this is something that none of you will have heard about. Anybody here know Serge Pinault? Used to be at Laval. Before that he was in Penticton, and before that he collaborated with me in Cambridge. We wrote a paper many years ago, 78, on disks of material, with material going round and round like that, and material, to make it easier, we took what's called a counter-rotating disk, which is a disk of material going round and round like that, superposed with one going round the other way. So it's 2 streams of material, one going round one way, the other going round the other way. And you can solve the problem of these disks, well, rather general disks in general relativity, and what their gravity is. And if you take the limiting case of those, where first and foremost, instead of taking a constant velocity of circulation, I mean a velocity, not an angular velocity, a constant velocity of circulation, and just stopping the disk somewhere, that would give you what my supervisor Leon Nestel would call a Mestel disk. But instead of stopping that, you let it go on forever. That gives it infinite mass, which might worry you, but nevertheless, if you let it go on forever, and then you take the limit when v equals c, so these two streams are really streams of photons going equal and opposite directions round and round, you find a very remarkable thing that was pointed out to me by Joseph Katz from our solution, which is that up there, and of course down there, R mu nu sigma tau, the Riemann tensor, is 0. Now that, of course, might make you feel that there was no gravity field there because it's flat. But no, that's not true. The Riemann tensor is 0, but it's 0 in axes that are, it's the normal flat space metric in axes that are accelerating upwards. So it's actually a Rindler space above, with axes accelerating upwards, and below it's in axes accelerating downwards, which of course means that there's a perfectly good gravity field, as I would say. It's there and here. I don't know what the official relativistic statement is about this metric when you think of gravity only as the gradients of this thing, because it's 0 on both sides. But it's absolutely clear to me that things fall from above and things go upwards from below. So I hope you'll agree with me that there are cases in which the standard relativistic way of thinking of things is probably wrong or not very illuminating. Now, where did I start?
13 past. So we'll go to 10 past.
Okay, all right, fine, thank you. In electricity, there's one quantity that's conserved, which is the charge. In gravity, you have mass energy conserved, you have all 3 components of momentum conserved, and all, if you like, 6 components or 3 components, depending on what you think about it, whether it's relativistic or not, of angular momentum conserved. And if we want to do experiments, which are, the aim of this is to do thought experiments on what's happened, following Ampere, you need to have a current to do the experiments on moving charges. And so we wanted to have an energy current for moving energy and find what sort of attractions or repulsions you get from moving currents of energy. But there's also the question, what about currents of momentum or currents of angular momentum? What are the sort of forces you get when you have these things moving? And that, I think, is the concept behind this talk, is you should, as it were, think of yourself as being Ampere, think of yourself as doing these new sort of experiments, but on gravity rather than on electricity. And that, I think, is quite fun to do, and that's what we're doing. Now, if you want to study currents, you need either a current loop, which is always a bit difficult because it's got complications to it, or you need a cylinder or something like that that's going through. And cylinders are reasonably easy in general relativity. So I'm going to take a hollow cylinder and cut it somewhere. And if I cut it somewhere and use a z equals constant cut all the way out here, of course it will be true that because the space out here, space in here is actually flat. It's quite normal space. But the space out here is actually a bent space because the cylinder's got mass. And this is a static cylinder at present. The cylinder's got mass, and as a result, the ratio of radius as to how far I've gone outwards to how far it is to go round won't be pi any longer, or 2 pi. And as a result of that, it is possible to draw a new surface. And in this diagram, take this m equals a fifth one to start with. M is a mass per unit length. It's a parameter that Levi-Civita invented for studying cylinders. Here is the flat space out to there. and there pi is its normal value, you have to measure the radius out to which you've gone by going along here, and then along here, and then the circumference is measured that way. So this is an invented thing, just a graph to measure the radius, as it were, the circumference. This value is the radius of the circumference, and this value is the radius measured radially. Is that clear? Or anybody who wants me to say something again, please raise a hand or do something, because this is essential to what comes on. Well, here we are. If you put the mass per unit length in the cylinder at Levi-Civita's m equals a fifth, it's not very bent, and you're reasonably happy with it. When you get to m equals a half, it goes up a bit. You might think that that doesn't matter very much. However, let's look at the circular velocity. And if you look at the circular velocity, that is the velocity of a particle that's going in a circle around the cylinder. Well, of course, cylinders, just like it is in Newtonian mechanics, cylinders attract not like 1 over r squared, but like 1 over r. Because is it where you see more of the cylinder as you go further away. So cylinders, as you can see from Gauss's theorem, attract in this way. And that, of course, means that if you balance v squared upon r against something that goes like 1 over r, that means that the velocity that you would have to, the circular velocity you would have to have is independent of how far away you are. And so this is a useful thing. And here we are, the v over c, which you measure in this space, has this formula to it. And you can see that as m equals a half, v equals c. So this thing that looked not terribly bent, it's really highly relativistic. You have to go at the velocity of light to withstand the gravity of this cylinder. Well, Embacher, who was one of the first people to have a look at these things and try and said, okay, well, it's clear that you shouldn't go further than this. That doesn't make good physical sense. But he was quite wrong. Because, as you know from studying Schwarzschild, V equals C at R equals 3m, not at R equals 2m. And you don't believe that the region between 2m and 3m is unphysical. So you can perfectly well go beyond, and indeed there is a physical limit that we'll come to later, which concerns the ratio of the mass on the cylinder to the pressure that's around it to hold it up. Because the cylinder has to be, we've assumed the cylinder is static and in equilibrium, and so there has to be a lateral pressure that's going round and round that to hold the cylinder up. Now, if the velocity of sound around that cylinder is faster than light, that won't be a physical cylinder. So there is a condition there, which is one of the energy conditions, which tells you that the cylinder is realistic, and we'll come to that in a moment. But you see there's perfectly good things that go on here. Very interestingly, when you get to m equals 1, you find that this drawing has made a cylinder again. But this, of course, isn't in a real space. It's just that as you come out here and you go further out, the ratio that you need is got by measuring this and then that for your radial distance, but you get the same circumference however far you go. Is that okay? The same circumference however far you go in radius. That's the way it is. Well, lots of people think you shouldn't go beyond here, but let's go on a bit. This is all just explaining to you something about Levi-Civita's metric, which is something in the 1920s. What we've been doing so far is studying things which actually Levi-Civita didn't realize, but that this, I've written down the metric in a form that's appropriate to nowadays. Levi-Civita had this C equals a 1, and it was the simplest case, and it corresponds to no vertical stress along the cylinder. The cylinder holds itself up by tangential stresses, but it just hasn't got any stresses up and down the cylinder. And so what we've been doing in the next picture is we've actually been studying these C equals 1 things as a function of this mass that goes on all the way out. And you can see when you've got to m equals 1, you get to the fact that this p phi divided by the sigma is the mass density on the cylinder, and p phi is the pressure round and round. So this is where the physics ends, because the energy condition is that p phi should be less than or equal to sigma. The pressure should be less than or equal to the surface density, mass surface density. So they'll be unphysical if you go beyond that. But here I've got a new class of things, because I've here included the possibility that there is a pressure along the cylinder. And you can see from this that if you go to tensions along the cylinder, that is not up but down, then you can get from m equals 1 to m equals 3/2, and you'll only fail at m equals 2. That is, you'll only reach the edge here, which is p over sigma equals 1. So this is for pressures going down, as it were, and this is for pressures along going up, and this is for pressures becoming tensions and going down.
So if p over sigma is equal to -1, you end up with flat space.
P over sigma equals -1. I'm not sure you end up with flat space. This one is actually called flat, and it has R mu nu sigma tau. I mean, it has, yes, this one, m equals 1 is actually flat. And it's flat in a funny way. It's flat because the cylinder is flat. So it's flat space, but in the regime in which you come round and it's a cylinder. But that's one of the strange things you meet, that in studying cylinders, that if you go to m equals 1, this point here, this is actually a flat space, but it's flat in the sense that if you went round by, it's periodic but flat, like a cylinder is.
The triple one-dimensional solution in GR for a point mass with equal negative tension is just the cosmic string metric, right?
Yes, that's correct.
So we have to reproduce that, don't we?
Probably. I haven't studied this metric. I'm not sure about it, but I'm telling you about this one. Yeah. This one is the one that has periodic, but is flat.
All these lines that
oh, down here.
Sigma
oh, yes, that's very likely. That's very likely.
So I'm confused what's going on there. Yeah.
All right, well, that is probably right. I'm sorry I haven't, but I must get on, otherwise we won't get to. This is what you get by studying what happens when you fix the mass, as it were, on the cylinder, and you look at different pressures. And you find that as you increase the pressure, you get to, well, Pz over sigma is -1. You get a lot of curvature in the space by going up here. And that's because you've got a lot of tension. So the tension actually has the effect of making the space more curved, but it actually, in a sense, increases the gravity, whereas pressure has the opposite effect and pushes you down in this So those things are equal and opposite. The pressure is going one way and the gravity is going the other. Now what I'm now going to talk about is what happens when there are actual currents of energy. These different gauges I introduced you to a bit earlier. So if you take t as t squiggle, a new time, you again, the metric takes the same form with the new time. And as I say, the gamma and the psi are left unchanged, but the t goes to a t squiggle and the a goes to an a squiggle. And here is what a does when t has done that. And you'll find, of course, that this thing is just the same. And you can define, if you like, an antisymmetric field tensor, which is the skew derivative, same as you would in electromagnetism, and then write things this way. And the related symmetric tensor k mu nu, where this is a plus, but that is going to be 0 if you take this to be the Killing vector of the space, because that is the condition that the space is stationary. And so for all stationary spaces, this k mu nu, the thing with the plus there, is just 0 because psi, there are no changes in the metric as you move along psi, because psi is, everything is stationary. And you can prove this thing is true generally, whether k is 0 or not. And you can define these quantities, an electric-like field or straight gravity field, as it were, which is this F mu nu related to the Killing vector this way, and H mu nu, which is related to the Killing vector that way. And you can redefine everything with B field is an H field, like psi cubed. And then this is you can re-look at this F mu nu and redefine it in terms of E and B or in terms of E and H. Why have I introduced these fields? Well, basically, curl of A is something that has 0 divergence in, well, what do I mean by 0 divergence? I mean that in this metric defined by gamma, which I consider to be the metric of space as opposed to space-time, in that metric I can define curl, div, and grad in a very normal sort of way, and it's in that space, which is normally fairly flat, but not very flat. It's space as opposed to space-time, and in that metric you can define these fields. And so here we are, and Einstein's equations now take nice forms. B is curl A. Div B is therefore 0 because it's the curl of something. And if you go to curl H, where H is just psi cubed B, you find this very nice equation that curl H is minus twice this kappa is 8 pi g over c to the fourth. And you get this equation with the components, the off-diagonal components of T, which correspond, of course, to the current. And this is indeed a conserved current. If you take the divergence of this curl, you, of course, get the divergence of this equal to 0. So this is the current flowing up the cylinder, as it were, if we took the cylinder as an example. And this is exactly what you would think of as being like curl H equals 4 pi j. You've got a minus sign, which is sort of expected, because that's the difference between like charges repelling and like masses attracting. And then you can do all these different things as you will, and you can get an equation for the 3 force, which looks very like the equations that you might have written down. But note that m, this is on the energy, as it were, of that mass. This is the ordinary gravity, and this is the gravomagnetism part of things. So electrical ideas and lines of force, if you like, and E and B help us to understand the forces due to energy currents, and you can make gyromagnetic, gravomagnetic solenoids, if you wish, by having cylinders that rotate or any of these sort of things. You get gravomagnetism, or cylinders that move upwards. You can have also. Well, Bonner in 1969 studied the gravity of a beam of light, and the equations, remarkably, provided all your light is traveling in one direction, the equations you have to solve turn out to be linear. And one of the few cases in general relativity in which the full relativistic equations are actually linear. And so parallel beams of light do not interact. This is sort of important. I mean, if your parallel beams of light had attracted, you might think, well, Lord alone knows what happens if you've got a star or something a very long way away and its light started doing this sort of thing, but it doesn't. And interact gravitationally. Well, you might have thought that there's energy in each beam, so well, beams ought to attract. So why don't they? That's part, but not quite all. I mean, the next slide, I think, tells you exactly that. Bonner's metric is here. It was in this form that Bonner wrote it, but I've tried to put it into the same form that we've been using for studying cylinders. And you've then got Xi of this form. M is the unit energy. The force needed to keep a particle at fixed xy is this thing. It's E plus this thing. But Norm, perhaps you didn't expect this thing. Why is that third thing there? Well, when I say I've got a cylinder here, and you take a line at constant xy or whatever here, you thought that that line, it's a constant distance and all the rest of it, you thought that that line was straight, didn't you? But it isn't straight. There's a metric in here, and it depends on r. And as a result, you find that that line, although it looks straight, is actually bent that way. And as a result, a thing traveling up that line will have a centrifugal, will have a force on it as it goes along the line, just because the line, although it looks straight, is actually bent. And that is this third component of the force. And if you put them all together, you find that the formula that you get for a thing moving at velocity v is this visible? Anyway, it's this formula. And so first and foremost, you can see that if v equals 1, which means the velocity of light, this would more than cancel this, so you would get no force. That's Bonner's result, that parallel beams of light don't attract one another at all. But if we now take anti-parallel beams of light, then this v is -1. And then you'll get, what, 4 times as much as you thought, or something like that. Anyway, you get a remarkable fact that beams of light traveling in opposite directions attract quite strongly, whereas beams traveling in the same direction do not. So the net result is no force if the particle moves at c, or if they've got parallel beams of light, parallel to the light beam. Twice the Newtonian value. The Newtonian value is itself 2m over r, because we're dealing with cylinders for a static mass. And from this, you can actually derive the momentum transfer, as I said right down near the beginning, if you consider the beam of light as the form of gravity and the particle here as being pulled, then you can work out the bending of the light beam that would result from the presence of the particle by transfer. That's from the momentum transfer. Interestingly enough, in the normal way, you get exactly the normal formula for the bending of light. Interestingly enough, if you do the normal formula from the bending of light, you get half the result from the psi, the coefficient of dt squared, and the other half comes from the bending of space. If you look at it this backwards way, it all comes from the psi. Anyway, that's just an interesting fact.
Can I put this a different way? I mean, again, going back to the cosmic string, you have T00 is equal to minus T33.
Yeah?
Now here you have a T00 is equal to T33.
Mm-hmm.
But you also have a T03, I guess. Is that somehow playing?
Yes, that's correct.
And that's what helps do the cancellation.
Yes, yes. Mm-hmm. Yeah, absolutely right. Now this is fun. This is a bit that's I think is slightly new. Suppose I haven't really got a cylinder here, have I? But still, perhaps I can do it on this. If I bend the ruler that way, I can make it so that it would like to twist, but I'll hold it so that it's actually got a torque on it. Now, I should have told you this in the earlier case. When you have something with a torque on it, that is actually a transfer of upwards angular momentum upwards, or a transfer of downwards angular momentum downwards. And they are the same. So a static thing with a torque on it, you can see that if I put something on the top there, I could make it twist by twisting the bottom. And so it transfers angular momentum upwards to the top. And if alternately I put something on the bottom, it would transfer negative angular momentum downwards. Anyway, the question is, what do you get if you take a twisted cylinder and look at what it does to things? And you find that inside the cylinder, again, space is flat and nothing happens. But now outside the cylinder, you've got a problem because you've got to fit these stress tensors. And this is a case in which I put a large, relatively large longitudinal stress on this thing. And this is just the lateral stress is just sufficient to hold the cylinder up. But now, because I've twisted it, all the stress tensors look like this at every point on the cylinder. And now I've got to fit this outside space onto this twisted cylinder. And as a result, I have to twist not space-time, but now I've got to twist space outside in order to fit this. Now you might have thought that I have to find a totally new solution of Einstein's equations. But I don't. And that is because of the wonders of Levi-Civita's metric. Levi-Civita's metric has got 3 killing vectors. And by combining them in different ways, you can find that you just have to take a different slice of the same metric and you get the solution. So basically, here is phi and here is z. And instead of taking the standard, this is 0 and 2 pi and 4 pi and 6 pi and 8 pi, instead of taking the standard slice up here by 2 pi, you have to take a slice like that. And then you find that you've got a solution that you can fit onto your inside through that twisted stress tensor that I drew. And it's fun to take an orbit in this thing. So here is an orbit, and you take an orbit and the particle it just goes within the cylinder, just goes straight out. I've drawn one that goes straight out and up a bit, because this is, so that's why there's a slight difference there, is that I gave the particle a slight boost along the cylinder, and once it comes out into this space, and it doesn't change its angular momentum at all, but nevertheless it moves around the cylinder because the space is twisted out there. And so when it comes back into the cylinder, it actually comes back at a different azimuth, although it's got no angular momentum. And it comes back in, and then it goes straight back in, or straight back in, but it's still got this slight boost along the axis, so it comes back in a different place. This twist would not have, is a twist in phi z, and therefore it does nothing to the planar orbits, the ones that stay in the bottom. That's why I had to give it a little shove along the z-axis, otherwise I'd have got a zero effect. I don't expect this interesting new effect to be discovered or observed ever, because it is very small and it's not very important, but it is new. And that's the only new thing that came, I think, out of out of this advocacy of looking at forces in general relativity. So astronomers found a flat, nearly closed universe from the CMB, not accounted for by matter and dark matter, and they also found an accelerating universe. Each independently fits well with the value of Einstein's lambda term, and therefore we think that that's a good description of what's going on. So it's consistent in a way that is great. And then the second conclusion I would like to make is that despite what some relativists say, I think gravitational fields of force are useful, and I think they're worth thinking about. And if you want something to keep you busy over lunchtime, I don't know how to define them exactly in non-stationary metrics. And I hope that's been fun. As I say, I can tell you why all this has a bit wrong with it, but we'll leave that for question time.
Does the twisting, this concept of propagating angular momentum up the cylinder, so if you took a light ray, would a light ray with only circularly polarized light have such a phenomenon as well?
I would expect that if you put a light ray with circular polarization going up, you would get this effect, yes.
And you can ask what would happen if you have two parallel light rays, both of which are either equally circularly polarized.
Well, exactly. There are lots of things like that, but it becomes, I think, a bit harder in those cases. But yes, I agree with you that all those are interesting cases now. Very interesting.
Equally spinning light rays would attract, or the oppositely spinning light rays?
Well, yeah, I perhaps didn't explain, well, light rays themselves don't attract at all, but that's ones without spin. I mean, Bonner did this thing with essentially zero mass particles rather than light, really. I mean, what do they call? They're called something. Scalars. What? Scalars. Yeah, all right. Scalar light, if you like. But anyway, there's a name that relativists give to zero mass particles with energy, but no. But I haven't. I mean, I agree with you. I thought about this, but I didn't solve anything in that.
So the Wald solution for a magnetic field in a Kerr space-time.
Yes.
Electromagnetic field in this Kerr space-time.
Yeah.
The gauge potential is proportional to Killing-Becker. I mean,
yeah.
the azimuthal Killing-Becker.
That's
so
right.
Do you get new types of solutions along those lines with these types of investigations?
The only thing that I got that was at all new is the thing that I got right at the end. We did look at the following case, which is new, but this we did before this work, Joseph Katz and I. Could I have a little more backboard, or is that? perhaps this is enough.
We can turn this off.
Here, well, we may need it again. Here is a torus, all right? It's going all the way around like that. And suppose instead of taking a static torus, I take a torus in which the inside moves up and the outside moves down. So it's a twisting torus in that sense. If you did this in electricity, you would know exactly what it was. It's just a solenoid that's in the form of a loop like that. And you'd know what the solution was. The solution is that there's a magnetic field running round and round inside, and there's no magnetic field outside. Well, the fact that there's no magnetic field outside means that if you do the same thing in gravity, you will find that there's no gravomagnetic field outside here. And because of that, it's an axisymmetric simple solution by Weil's method. So you can solve it out here, more or less whatever is going on inside. And what we did, to just give us a specific thing, was to say, well, we need a field in here that is a field with a gravomagnetic field. One of those is given by Bonner's solution, of course. So we cut a little piece of Bonner's solution and put it inside there. And that, of course, is inside here too. And it has the gravomagnetic field running round and round inside here, just as we want. And then, of course, we had to put in some very particular current distribution around this outside to fit it onto the static solution on the outside. And we did all that, and we published that in CQG a few years ago. This is Joseph Katz and me. And so we got a solution corresponding to a gravitational solenoid, a toroidal solenoid. I mean, for the solenoid that's a straight solenoid, that's relatively easy, and that's just a rotating Levi-Civita solution, which is in the books. But this one is nicer in some respects because, you know, this one's really finite. It's not got the problems. One of the things I should explain to you is that if you look at Bonner's solution for a light wave, that if you take the gravity of a light beam, you can't ever escape. The gravity of the light beam goes on and on and on and on and on. And you can't escape. There's no velocity of escape. It goes on forever. So light beams are incredibly attractive looked at from that point of view. But they have to be infinite, of course. Right.
Do you have a question, Dick?
Well, it was sort of a general one. So there's all of this magnetic field intuition and dynamos and all of that, and rubber bands, etc. So are you now thinking about those aspects of gravity in that form? Is it really completely one-to-one?
It's, as far as I know, totally one-to-one, but I don't quite know how to do it inside the ergosphere. Because what I've told you has lots of xi's in it. Xi goes to 0 on the ergosphere. But yes, I mean, if you look at the stresses in a magnetic field, there's a push along the lines of force, there's an attraction at right angles, just like in magnetism. There is I mean, this is gravomagnetism. There's a push along the lines of force and a pull at right angles to the lines of force. That's for the magnetic bit. But you've got also the electric bit. And of course, if you take I told you that two currents of electricity attract one another, and two currents of energy repel one another. But of course, that's to be added to the fact that unfortunately, or perhaps fortunately, you can't just have the current in gravity, you've also got the mass, and the mass is attracting. So in practice, most times, not in Bonner's case, but most times, you can't beat the attraction with the repulsion. But you've got the repulsion, but it's smaller normally than the attraction. Another way of looking at these forces that I've been talking about is there in Landau and Lifshitz, but it's not in these words. But they compare the orbit of a particle following a geodesic in space-time to the orbit of a particle following a geodesic in space at constant velocity. And the difference they call the gravitational force. Now, the one thing that I have which is against Landau and Lifshitz is that suppose you put in forces that exactly counteract these gravitational forces. So the extra forces with little bits of string attached to the particle. Then you might expect that the particle coming in from infinity and going out to infinity ought to have, since it's had no gravitational force according to Landau and Lifshitz, it ought to come out in the same direction as it went in. But that, according to Landau and Lifshitz, ought to be a geodesic of space as opposed to a geodesic of space-time, since it's the geodesics of space that they take as the fundamental things. But if you look at the geodesics of space, particles coming in along one don't go out in the same direction. So there is, what Landau and Lifshitz has done is to take the full geodesic equation, transfer certain of the terms onto the right-hand side. And I think they haven't transferred quite enough. So those they call the forces, but I think that there is an extra force due to the bending of the space itself rather than the space-time. But I'm going to stop there.
Okay, we should thank Donald McGinn and go upstairs and have some